Okay, now let's look at another example of calculation of work done. Now we have a 30 kg slender rod starts from rest at the position shown. So determine its angular velocity after it has rotated 4 revolutions. So this is the distance that the rod has rotated. So this is the key that we have to use in order to calculate the work done. All right, we always start by drawing the free body diagram. Okay, so this is the FBD, the free body diagram. And notice that in this chapter, you don't have to draw the kinetic diagram anymore, because the kinetic diagram indicates the component of mass times acceleration, ma, as well as I times alpha. But in this case, we are not dealing with the Newton's second law of motion. We are dealing with work and energy method. Okay, so by looking at the free body diagram, we know that the moment, couple moment here is doing work because it undergoes rotation. There is a change of angle. There is angular displacement. Okay, so what is the angular displacement? Is basically the 4 revolution given up here. Okay, the 4 revolution means that one revolution is equal to 360 degrees, which is equal to 2 pi in radian. So you convert it to radian. So you will get 4 revolution equals to 4 times 2 pi, which is equal to 8 pi. Therefore, the angular displacement delta theta is 8 pi rad, and we can then calculate the work done by moment. This is the work done by couple moment m, which is m times delta theta. So it is equal to 20. Moment is given as 20 Newton meter times 8 pi. You have 502.65 joule. I forgot to mention in the previous video that this is the unit for work, which is joule. Unit for of work done, which is in joule. Okay. Okay. The next thing is if you look at the weight here, the weight mg, after the rod has rotated 4 revolution, you imagine the rotation of 4 revolution of rotation, it still remains at the same point. So let me do this again. I will erase this. Okay, and basically for mg, we are looking at this point, the center of gravity g. So basically center of gravity, after it has rotated 4 revolution, it still comes to the same point, and therefore delta y is equal to 0. Okay, and because of delta y equals to 0, the work done by the weight is also equals to 0. So no work done by the weight. Now let's look at the force P1 and P2. Are these two forces doing any work? There's a clue given in the question. It says the forces remains perpendicular to the rod. What does this mean? This means that these two lines are the path of motion of the force P1 and P2. So if you imagine throughout the motion of this rod, P1 and P2 will remain tangent to the path or remain perpendicular, remain 90 degrees. It remains 90 degrees throughout the motion. So these are 90 degrees. This is 90 degrees. For another motion, this is also 90 degrees to the rod. So that is what it means by the forces remain perpendicular to the rod. So in this case, are these two forces doing any work? Yes, because it remains perpendicular. Therefore, the force force P1 and P2 actually travels in a circular path. So this is the path, the delta S for P2, and this small circle is for P1, delta S for P1. I'm going to write delta S for P1 over here. Okay, so how do we calculate it? We will be using the equation for work done by force, which is the force times delta S. So U P1 is equal to P1 times delta S1. What is delta S1? Is basically the circumference of the circular path, and you have delta S1 is 4 pi. Okay, so you have UP1 equals to 30 times 4 pi. All right. How do you get this equation? This equation here, S equals to R times theta, is the equation that you have learned in trigonometry. Okay, this is called a sector. So if you are wondering how this equation comes about, you can go back to your mathematics and look at the trigonometry chapter and look how to calculate the sector. Basically, the sector is something like this. It's like a pizza. Okay, so you have S over here, and this is theta, and this is R. So the relationship between this is S equals to R times theta in radian. All right, so that's how you get UP1, which is 377 joule, and for UP2 it's the same. P2 multiplied with delta S2. So delta S2 is basically the circumference of this big circular path. So it's R2 times theta, which is 1.5. With the radius of the big circle, multiply with 8 pi, you have 12 pi. 8 pi is taken from this 4 revolution over here that we have calculated earlier in the calculation. So in the end, you will get UP2 is equal to 754 joule. Okay, so that's I have demonstrated several calculations of work done. In the next video, we'll be calculating the angular velocity using the principle of work and energy.